Have you ever stopped to think about what really separates a simple script on your laptop from, say, the massive systems that run our banks or our power grids? Well, the answer is a lot more than just a few extra lines of code. It's an entire discipline. Okay, let's get into why we absolutely need to treat building software less like casual writing and more like a high-stakes engineering project.
First things first, we've got to get a key concept straight. We toss around the words code and software like they're the same thing, but they're not. They're actually fundamentally different, and honestly, getting this difference is the very first step to understanding what software engineering is all about. So here it is. Software isn't just the computer programs that code itself. It's the programs plus all their associated documentation. Now, that second part is what everybody forgets. Think about it this way. The code is the engine, right? But the documentation, the user manuals, the design specs, the architecture diagrams, that's the blueprint. It tells you how the engine works, how to fix it when it breaks, and crucially, how to make it better later on. Without it, all you have is this incredibly complex machine with no instructions. And this whole distinction becomes absolutely critical when you start talking about scale. See, programming in the small is what most of us do for a personal project or a quick script. It's usually just one person, it's for a limited time, no big deal. But programming in the large, that is a completely different beast. We're talking about building systems that are meant to last for years, worked on by huge teams, and used by thousands, if not millions of people. The kind of casual, I'll just wing it approach that works for a small project, well, that will lead to absolute disaster on a large one. Okay, so if we can't treat massive software projects like a personal hobby, what's the right way to think about it? Well, the best analogy, and the one we're going to explore right now, comes from a much, much older field of engineering. This right here, this is the guiding principle. Build software like we build bridges. When you hear that, what pops into your head? For me, it's words like discipline, reliability, planning, and, of course, safety. You just expect a bridge to work every single time, without fail, for decades. And that is the standard we should be aiming for with our most important software. But here's the catch. Adopting an engineering mindset, well, it isn't a silver bullet. Because even with centuries of experience, physical bridges sometimes fail, and they fail catastrophically. The key lesson here isn't just knowing that they collapse, it's digging in and understanding why. That's where the real learning happens. So let's take a look at one of the most famous engineering failures in all of history. It's a really powerful cautionary tale, not about bad materials or lazy construction, but about a fundamental and disastrous misunderstanding of the forces of nature. This is Galloping Gertie. That was its nickname. This is the Tacoma Narrows Bridge on November 7th, 1940. I mean, just look at it. It's not just breaking, it's twisting like a piece of ribbon in the wind right before it tears itself apart. This image became an absolute icon of engineering failure, and it's a lesson that's taught to every single engineering student to this day. So, what on earth went wrong? Let's break it down. The bug, if you want to call it that, wasn't just one single thing. First, the solid sides of the bridge basically acted like a giant sail, catching all the wind. It was also way too thin, which meant it could twist really easily. This created this terrifying feedback loop where the wind's vibration just kept amplifying itself. But the most important failure, the real kicker, is right there at the bottom. Bad testing. They tested the heck out of the bridge to see if it could hold weight, but they never properly tested how it would handle strong wind. They completely missed the environmental factors. Okay, so let's take that exact lesson, that failure to test for the real environment, and apply it directly to the world of software. Because our digital bridges, they collapse too, and for some remarkably similar reasons. I want you to remember this date, June 4th, 1996. This was the day of one of the most famous and one of the most expensive software failures in history. This is the very first flight of the Ariane 5 rocket. Less than 40 seconds after a totally perfect launch, it suddenly veered off course and was intentionally destroyed by its own self-destruct system. And the cause? It wasn't a bad engine or a fuel leak. It was a software bug. Let's walk through exactly what happened, because it was a stunning chain reaction. Step 1. To save time and money, the engineers just reused the guidance software from the older and much slower Ariane 4 rocket. Step 2. Here's the problem. Ariane 5 was way, way faster. That meant a number that was tracking the rocket's horizontal speed got much bigger, much faster than it ever could have on the Ariane 4. Step 3. That number eventually became too big for the little 16-bit space it was supposed to fit in. This is called an overflow error. Step 4. This one tiny error caused the primary guidance computer to just shut down. Milliseconds later, the backup computer running the exact same flawed software also shut down for the exact same reason. And finally, step 5. The rocket was now totally blind. With no guidance, its engines swiveled too hard, and the force literally tore it apart. And this right here just perfectly illustrates the point. A bridge twisting itself apart in the wind, a rocket exploding in the sky. One is a failure of aerodynamics, the other is a failure of data conversion. But at their core, both are fundamentally failures of engineering. The engineers of the Tacoma Bridge didn't properly test for wind. The engineers of the Ariane 5 didn't properly test their old code under the new, faster flight conditions. In both cases, the system was destroyed by an environment its designers simply failed to account for. And that is why we need a formal discipline. We need a set of proven theories, methods, and tools designed specifically to prevent these kinds of catastrophic failures before they can ever happen. Look, building things with code has its own unique set of challenges. Unlike a steel beam, software is totally abstract. You can't touch it. It's not governed by the laws of physics that we can see and feel. A tiny change in one little part of the code can cause massive, unforeseen consequences somewhere totally different. All of this makes it incredibly complex and unbelievably expensive to change once it's been built. And that brings us to the most crucial point. Software engineering isn't just about writing code. It's a full-blown engineering discipline that covers all aspects of making software. What does that mean? It means from the very first spark of an idea, through the design and specification, the development and testing, all the way to maintaining that system for years and years after it's been released. So what's the end goal of all this work, all this discipline? Well, it's to create good software. And that means building software that can actually adapt to future needs. Software you can truly trust with your most important information. And, software that's actually easy and intuitive for people to use. It's about engineering something that doesn't just work on launch day, but works reliably for years to come. So I'm going to leave you with this final thought. Think about it. Your banking app, the power grid, the traffic control systems in your city, the medical equipment in hospitals. Our entire modern world is built on a foundation of software. All the systems we rely on every single day are bridges built from code. So the real question is, who engineered their bridges?